So, dear colleagues, good evening. And first of all, I would like to thank. Okay, like that. I would like to thank the organizers of this nice conference in such a beautiful spot for the invitation, and for giving me the opportunity to convey you some of our most recent investigations, which were devoted to shed light, so to say, on the charge dynamics of an interesting family of correlated non-centrosymmetric and magnetic Weyl semimetals. Let me try, first of all, to briefly introduce the topic of my presentation, yet from a broad perspective, but mainly with the goal to set the stage for the motivation of our recent investigations. The last decades vividly witnessed the fundamental discoveries of relativistic phenomena in solid-state topological materials. This is because of the presence of a direct state in the electronic structure of this system, which is characterized by this cone-like, I don't see it. Yeah, okay, it's very small. By this cone-like shape, because of the linear dispersion relation in the reciprocal space, and the two cones merge actually in one single massless point. Now, by breaking space inversion and or time reversal symmetry, you can lift the degeneracy of the direct cones. So basically, you can shift in energy at the same momentum, or to make a shift in momentum space at the same energy of the direct cones, so that you have or you create a pairs of direct cones, and this is known as the Weyl state. Now, most recently, the research focus actually moved to the understanding of the link and interplay of magnetism with respect to this topological state. This is not only of fundamental importance, but also for possible technological application, particularly when designing novel electronic devices. I'm thinking here to the broad field of spintronics. Now, this particular topic has been boosted by the discovery of non-collinear antiferromagnet, as well as Kagome ferromagnetic semimetals, but most recently, another family of materials attracted some interest in the community, and upon which I would like to focus my attention today. These are the so-called non-centrosymmetric rare earth aluminum germanium compound, and this system indeed breaks by their own the space inversion symmetry, and from first principle calculation of the electronic structure, you can predict, for instance, the density of state for the majority and the minority spin bands. So you can see that there's a perfect balance between the two density of states for the lanthanum compound, which is an empty F orbital materials, and this support the non-magnetic nature of this system. But there's an imbalance for the cerium and the praseodymium compound, which indeed are predicted to be ferromagnet. The magnetism in the cerium compound is somehow debated in the literature, but there are robust evidence that the praseodymium compound is indeed a ferromagnet. Now, this system provides an interesting arena, because upon rare earth substitution, therefore by circumventing doping, as predicted by first principle calculation, you can study the formation of topological, mainly Weyl state, sitting very close or even at the Fermi energy, and therefore this state should contribute also remarkably to the DC transport properties. You have mainly Weyl state, eventually of both type 1 and type 2, depending from the effective tilting of the direct cone from where the Weyl state originates. Now, these materials are of interest also because in the ferromagnetic ground state, particularly for the praseodymium compound, on the top of the broken space inversion symmetry, you also break the time reversal symmetry, which will have important consequences as far as the DC transport properties are concerned. Now, our motivation was to address this family of materials from the perspective of the charge dynamics. So by looking basically to the optical properties, revealing some signature and fingerprints for the presence of this topological state in the electronic structure, but also to have access two quantities, which allows us to establish the link or to look into that interplay between magnetism and this topological state. So our experiment consists in measuring, first of all, the optical reflectivity over a very broad spectral range from the far infrared to the ultraviolet, so on a continuum of frequency and as a function of temperature. And this is indeed a prerequisite in order to perform reliable Kramers-Kronig transformation, from where you have access to all optical functions. And for today's presentation, I'm going to focus on the real part of the optical conductivity, which is notably well-known quantities to describe the absorption spectrum in condensed matter. Now, the focus will be mainly on the praseodymium compound, which, as I said, is a ferromagnet below a Curie temperature of 15 degrees Kelvin. From the magnetic susceptibility, there are evidence for a Curie Weiss temperature, which is double as large, about 30 Kelvin, and the magnetic ordering is due to a magnetic coupling acting as a Zeeman field between the local moment of the F orbitals along the EZC axis, which is the C axis, indeed perpendicular to the layer AB plane. Now, the praseodymium compound can be really considered as the magnetic isochemical substitution of the non-magnetic, noncentrosymmetric lanthanum compound, which I'm going to consider as a reference materials. As I said, is an empty F orbitals materials, and therefore is going to provide values or quantities which correspond to the bare band values. So this I would like to focus now on the real part of the optical conductivity, particularly spanning the energy interval from the far infrared up to the mid infrared, and look into the temperature dependence, which in that spectral range will have some direct link with the ferromagnetic phase transition, as I'm going to argue later on. So what we have here, there are basically two features. There's a zero resonance, so a zero energy mode, which correspond to the effective metallic contribution to the optical spectra. This is going to be later on a global Drude resonance, which actually narrow with decrease in temperature. And then, as interband excitation, there's this very strong far infrared feature, which is actually quite broad at higher temperature. Upon lowering the temperature in the paramagnetic state, we observe, first of all, a narrowing of this feature, and then upon crossing TC, going into the ferromagnetic state, as I'm going to show you later on, there will be a suppression, depletion of the high-frequency shoulder of the feature, which then leads to a redistribution of spectral weight, accumulating in these cusp-like far infrared absorptions at low temperature. Now, we also observe some spectral weight reshuffling, however very smooth and moderate, from the mid-infrared up to the near-infrared without any specific anomalies with respect to the ferromagnetic phase transition. And then at higher frequency, all the spectra merge together in a series of interband transitions, which are all temperature independent, and which correspond to excitation from state far away from the Fermi level, so deep into the electronic structure across the Fermi level itself. I would like to focus the attention particularly on this far infrared feature, and it could be instructive to completely decouple or disentangle that feature from the total optical conductivity. In order to do so, you first need to systematically subtract the intra-band contribution to the excitation spectrum, so the effective metallic part of the optical conductivity. This can be done, for instance, by describing, first of all, the measured spectra within the phenomenological Lorentz-Drude approach, which is a very common tool in optics in order to identify the various contributions which affect the optical conductivity itself, which indeed is an additive quantity. So what we did consider here, two Drude terms, a narrow and a broad one, accounting for the multi-band nature of this system. But later on, these two Drude terms will define the global Drude resonance for the optical spectra, and then a series of Lorentz harmonic oscillators for the final frequency excitations. The higher frequency oscillators are temperature independent, and I will particularly focus the attention here on these two first harmonic oscillators, which fully shape the far infrared feature, namely this strong interband contribution in the far infrared. I don't have time to go into technicalities about this fitting procedure, but I would like to point out that this is really a minimal approach in order to describe the measure spectra. And also we did apply the very same fitting philosophy for all members of this family of rare earth aluminum germanium compound. So whenever performing a comparison between different compounds, particularly with respect to quantities which eventually profit from this type of phenomenological analysis, we believe that that comparison is reliable because based on equal footing. Now, first of all, as I said, you can define out of this procedure the global Drude resonance, which is shown here, for instance, for the low temperature. Then you can systematically subtract that intraband contribution from the optical spectra, and you are left with the clean interband contribution in the optical conductivity, which is shown here as an example at the lowest temperature. And here we immediately recognized a first important feature in the optical spectra, namely that the low frequency tail of these far infrared absorptions is characterized by linear frequency dependence. And this is a pretty well recognized feature in a large variety of topological materials. It is directly related to the linear dispersion relation in the reciprocal space related to the direct cone from which indeed the Weyl state originates. Now, what is eventually peculiar here is that we have just one single linear frequency dependence without any kink in between. This is also an indication that the Weyl state, as predicted by band structure calculation, are of type 1, so the direct cone are not tilted. And then you may also observe that this linear frequency dependence cut the frequency axis at a finite frequency. This is an indication for the presence of tiny massless gaps at the direct cone themselves. And this could be due to the reinforced virtue by spin-orbit coupling, particularly at low temperature, or a consequence of correlation effect in the spirit of the Weyl mode scenario as predicted theoretically. But beyond that, let me mention that evidence for gapped Weyl nodes was also provided at selected location in the Brillouin zone in the reciprocal space by the ARPES investigation, which indeed directly imaged the electronic structure. That linear frequency dependence has some importance in another, from another point of view, namely it can be shown that the slope of that linear frequency dependence is inversely proportional to the Fermi velocity. So we can extract the Fermi velocity as a function of temperature, which is shown here from the charge dynamics, from this interband contribution, identifying that absorption feature as a feature of topological nature. And here is the results for the praseodymium compound. There's a very weak depletion from higher temperature. Otherwise, the Fermi velocity is very low and flat and temperature independent. In the paramagnetic state, then we observe a sudden enhancement here, however, very moderate upon crossing the Curie temperature going into the ferromagnetic state itself. It could be now, it is instructive now to compare these results with what we got as far as the temperature dependence of the Fermi velocity in the lanthanum compound. This quantity was obtained after the very same procedure, and the behavior is very distinct. In fact, the blue dashed line here is not just a guide to the ions, but corresponds to a temperature, to a logarithmic temperature dependence of the Fermi velocity, which is indeed the expected, from a theoretical point of view, this can be predicted for weakly interacting topological materials. And from a theoretical point of view, that logarithmic divergence is supposed to vanish as soon as correlation effect play an important role. Indeed, we believe that that strong suppression of the Fermi velocity between the lanthanum and the praseodymium compound at low temperature is an indication for the important role played by correlation effect in these materials. And in fact, this renormalization of the Fermi velocity between these two compounds actually goes hand in hand with the very equivalent renormalization of the kinetic energy, which is directly related to the Drude weight, namely the spectral weight encountering the effective metallic contribution of the optical spectra, and which imply also a very important enhancement of the effective mass of the itinerant charge carriers in the praseodymium compound with respect to the lanthanum one. Obviously, it remains to be seen whether a condo-like scenario, because of the hybridization of the localized F states with the Weyl state sitting or being very close to the Fermi level, may be promoted in order to account for that role of correlation effect or for the onset of correlation in these materials. However, that strong suppression of the Fermi velocity has been found also in many other correlated heavy Weyl or nodal line direct semimetals. Let me now insist a little bit more, or from another perspective, on this far infrared absorption. And let me point out, as I'm trying to show you here by this inset, that in fact the spectral weight of this resonance increases upon crossing or upon going into the ferromagnetic state. The spectral weight in optics is the integral of the optical conductivity in a finite frequency interval, and in fact what you see here, that going from the paramagnetic, the red curve, into the ferromagnetic state, there's an obvious enhancement in spectral weight, which we can systematically extract also with the support of our phenomenological fitting procedure. And it turns out that the spectral weight of, as you see here, we can in fact focus the attention on the low frequency first harmonic oscillator, describing the edge, the low frequency edge of that far infrared absorption. And within this approach, the spectral weight just corresponds to the square strengths of the harmonic oscillator itself, which, as you see here, increases going into the ferromagnetic state. So you can extract in this way the temperature dependence of the spectral weight, which turns out to be basically constant temperature independent in the paramagnetic state. But at the Curie-Weiss temperature, there's clearly the onset for a progressive enhancement of the spectral weight of this far infrared resonance, which I tried to convey you before, is topological in nature. The most astonishing result is that this goes hand in hand with the equivalent enhancement, so to say, of the anomalous Hall conductivity, which has been measured independently. These are just data from the literature with this DC transport technique. And the two dashed line here, by the way, are just guide to the eyes. So this means that, or may allude to a possible association between a resonance, which is topological in nature in the charge dynamics, with state characterized by a very large effective Perry curvature, which indeed is the prerequisite in order to get anomalous Hall conductivity. And I would like to further argue on that, and very instrumental in that respect are first principle band structure calculation, which were performed after the density functional theory, following a procedure which is indeed well established in the literature also for this very same family of materials. First of all, you can identify the position of the Weyl state in the paramagnetic and ferromagnetic state in the reciprocal space, and then we just selected a few of those Weyl states representative of region in the reciprocal space where these Weyl states gathered together and for which a Fermi surface was also predicted. Then we consider direction running nearby those Weyl states, and we calculated the band structure of these Weyl nodes, or around those Weyl nodes. And here I don't have time to go into too many technicalities or details, but I would like to emphasize something that you may observe by yourself looking to this data or to this calculation, namely that in the ferromagnetic state, the band structure developed some kind of asymmetry between the negative and the positive direction in reciprocal space with respect to the fully symmetric situation in the paramagnetic state itself. And this is going to have important consequence in the temperature dependence of the occupation function, which then determines the interband transition in the charge dynamics. You can also look at which are the most probable interband transition from a band structure point of view, and it turns out that in the paramagnetic state, the interband transition are grouped around two characteristic resonance frequencies, the red and the green bars here. For the ferromagnetic state, they distribute in a far-infrared interval of energies represented here by the blue bars. Now, from this calculation, you can then extract the real part of the optical conductivity, for instance, via the Kubo-Greenwood formula, which is shown here in comparison to the experimental quantity. Now, let me immediately warn you that this comparison is probably more reliable in the energy interval of about 100 millielectron volt around the Fermi level, because in that spectral range or energy interval, the impact of the F electron is not that pronounced and invasive in the electronic band structure, and this might explain some deviation at higher frequencies. But from the calculation point of view, so in that low spectral range, you see that in the paramagnetic state, there are actually two single resonance or absorptions, then going into the corresponding to those characteristic resonance frequencies, the green and the red that I was pointing out before. Then in the ferromagnetic state, we observe a depletion basically of the R frequency 1, favoring a spectral weight redistribution, so that basically you have a distribution of interband transition in the far infrared and an accumulation of spectral weight into this cusp-like feature in the absorption spectrum. And this copies rather well with what we observed in our experiment, at least as far as the redistribution of the spectral weight is concerned. Let me mention that the calculation was done at t equals 0 without thermal broadening, so we believe that indeed thermal broadening prevents us from an experimental point of view to resolve in the paramagnetic state that absorption into two single excitation. But more important than that is that from this calculation, you can then extract also the effective Berry curvature shown here for the ferromagnetic state within the y-x plane. The quantity is already integrated along the z-axis. And you see that that Berry curvature is very much enhanced. And interestingly enough, at location in the reciprocal space coinciding with the position of the Weyl nodes. Here the green dots correspond to the projection of those Weyl nodes within the y-x plane, and the black star are the selected one for our band structure calculation itself. And this brings me back to the previous result that I was emphasizing by the previous view graph, and I would like to reproduce here for the temperature interval below the Curie-Weiss temperature, where I did pointed out the relationship, or let's say the similar behavior of the spectral weight of this topological resonance in the charge dynamics with the anomalous Hall conductivity, which eventually is no longer a surprise because the anomalous Hall conductivity is supposed to be directly proportional to the integral over the Brillouin zone of the convolution of the effective Berry curvature with the temperature-dependent occupation function. So basically, we may say that this progressive enhancement of the spectral weight for that resonance in the charge dynamic, which is indeed topological in nature, indicate the empowered matrix element for the dipole active excitations in the charge dynamics, for which, in fact, a very large Berry curvature may be predicted. And this brings me to the conclusion of my presentation. I try to convey you that from the charge dynamics, we can reveal the characteristic features as far as the optical response is concerned, associated to the presence of topological state in the electronic structure. Particularly the linear frequency dependence here is a typical indicator for the linear dispersion relation in reciprocal space due to the Dirac cone from which the Weyl state originates. And the linear frequency dependence allows us to extract then the Fermi velocity, which is very much depleted indeed in the, with respect to what you get in the lanthanum compound, which is probably a sign of or an indicator for the important role played by correlation effect. Obviously, there's here an enhancement here which is, however, very moderate. This could be due to the fact that in the ferromagnetic state, the suppression of scattering due to spin fluctuation facilitate again the movement of electron, but nonetheless, that values are very much suppressed with respect to what you get in the lanthanum compound. But more important is probably the discovery of that spectroscopic link, so to say, between the spectral weight of that resonance in the charge dynamics and the anomalous Hall conductivity, which, as I said, was determined totally independently. And this indeed has an important implication in the sense that a very large effective Berry curvature associated to the non-trivial topological state and concomitant with the broken time reversal symmetry indeed may deem necessary in order to provide the environment, so to say, for a very large anomalous Hall conductivity in these materials as observed via a transport type of measurement. More details about this work can be found at this recent publication. And let me then conclude by acknowledging the great work of my team. I would like particularly to mention my postdoc, or my former postdoc, Run Yang, now at Stuttgart, my PhD student, Matteo Corasaniti, who is about to finish and defend his thesis on this topic in a month from now. And then we got very beautiful spacemen from Sidomir Petrovic at Brookhaven National Lab, and we enjoyed the collaboration with teams based in 3 different places, in Dresden, at Beijing, and even at the University of Fribourg in Switzerland for the DFT band structure calculation. Last but not least, I would like also to acknowledge the partial support of our funding agencies in Switzerland. And with that, thank you very much for your kind attention.
Thank you very much. And now questions, please.
Yes, Leo, thanks a lot for this very interesting talk. I have a question, right? I mean, you somehow said now, oh yeah, this change of the Fermi velocity is minor, but it's basically a factor of 3, and within at the phase transition, this factor of 2, which seems to me it's a lot. Is this really some kind of trivial thing? So there, the extracted Fermi velocity, right? I mean, it changes at the Curie temperature at 30 Kelvin, right? By a factor of 2.
Yeah.
That seems like a lot.
Well, as I said, one possible explanation for that is that when you suppress scattering by spin fluctuation because of the ferromagnetic state, and particularly also because at the ferromagnetic state, as I was trying to convey you, we have certainly a reconstruction of the electronic band structure. So this may obviously explain also this change. Nonetheless, the values by itself in absolute value remain pretty much depleted and very low with respect to what you get in the lanthanum compound, which for sure. So that was somehow my point. Mm-hmm. But I mean, maybe this is a speculation, what I just said, that by suppressing scattering by spin fluctuation, you facilitate the movement of electrons. But on the top of that, there's also a reconstruction of the electronic band structure, which is even more important in view to the very large Berry curvature, which then facilitate the anomalous Hall conductivity.
And then if I may, I have a second question. So now when you're fitting this, you're subtracting the both Drudes, and then you have this mid-infrared peaks, which basically you had like 2 of them, right? Well, if you had like 2 oscillators in the mid-infrared, so like L1 and L2, but you're basically just fitting both of them and you have this linear. So is this L2 so far away that you can neglect it, or does it play a role?
I mean, maybe I have maybe I have an additional view graph just to convince you that this is, probably is coming, yeah. Here it is. Okay, so here I'm comparing that with the lanthanum compound. And then you see that in the lanthanum compound, it barely changes in temperature. And by the way, if I just calculate the difference of spectral weight, for instance, at low temperature with respect to 100 Kelvin, which is large enough with respect to any magnetic phase transition, you see here, for the lanthanum compound, it remains flat. There's no change. But then there's a reshuffling of spectral weight between these 2 shoulders or these 2 oscillators, which is indeed an indication for the reconstruction of the electronic band structure because of the ferromagnetic phase transition. And in the lanthanum compound, which doesn't have any magnetic phase transition at all, I mean, there's absolutely nothing. And the two oscillators here are so distinct from the tail due to the intra-band contribution, through the light contributions, that basically, I mean, this is very trustable. I mean, you cannot just say that this change here is due to some kind of high frequency tail of the intra-band. I mean, they are very well separated, the two ranges.
Okay, thanks.
Yes, could you show us your last slide again, please, the one with the conclusions?
Yeah. Now I have to go up. Yeah. 1 second, should come. Okay.
Okay. So now here I notice in the blue curve there is a peak at 0 frequency, okay?
Oh,
and,
yeah.
Yeah.
Okay.
Now the question is, can you bring that into correspondence somehow with DC transport?
No. I mean, I think that this is probably somehow, you know, when you subtract. Okay, I could just claim it's a kind of spikes of noise because it's a very low frequency at 0. I mean, we cannot really measure down to 0. When you subtract the Drude resonance from the measured quantity, you might have some kind of. I would not pay attention to that.
So you have already subtracted the DC component to get this curve.
Yeah, I mean, this is the delta one, you see? This is already the, let's say, what I called clean interband contribution.
Okay, thank you.
I mean, yeah, probably you saw before, if I can go back quickly to the, here I'm coming. So you see, the Drude resonance in that one is definitely much larger. And then I subtracted that part here, the dashed line.
Okay. More questions? Well, if not, let's thank the speaker for wonderful talk one more time. Let's thank all the speakers of the session. And thank you very much. One advertisement. It's good that you came.
Okay, we have an announcement for the proceedings. So the journal where the proceeding will be published is open source, and there are some open source charge, but they are completely paid by the conference and the journal. So for all invited speakers, there is no fee for open source. And so this is the information. And in any case, if you are interested, you write to me, so I can help you. With the editorial staff is very nice, and they help you very much. Thank you for your attention.
Thank you.
And small contribution. Okay. Okay, we don't have many people in the audience, but you will have one copy of this in your room tonight after the gala dinner. So please do consider it. And second thing is, from my experience, high-level scientists like Laura, Erika, and Valerie don't write papers, and ask one of your PhD students. And it will be good for him or her. And let's have a very good, prestigious special issue published for the first conference on quantum materials and technologies. I think this is our common understanding.
Yeah.
Yes. Laura, we need your support. Erika and all. So, we may also announce the same thing when most people, we have the gala dinner here, so this place will be prepared for the gala dinner in 2 hours, yes? you will see the service sector in Turkey. So, so we will again announce this during the gala dinner, and enjoy your gala dinner tonight. I think starting at 8 o'clock. And this is what I will say. Yes, okay. Anything you want to say something? Okay, you are also co-editor.
Sorry? Yeah.
So you can say anything if you want to say.
Well, okay, so the idea was that we will have these small topical reviews on a, let's say, okay, selected topics, and, okay.
Yeah, we are opening for this journal the possibility to write a topical review. Topical review is a perspective where you have a single paper, but with a number of order of 5 or 6 people that write only 2 pages, 2-3 pages, or 4, from 2 to 4. And it will be a topical, it will be a single article with 4 sub-articles, like subsections, where each group is responsible for what they write. However, there is the 4 short paper are in a common topical review. And this is very important for the new perspective for young people and so on. And it's an intermediate between a review and a short paper. So it's been very successful in many different communities. In theory, very different theory group, mathematics, so all chemistry. So it's a new kind of review paper. And this is very nice because it's not a paper with 10, 20 authors for speaking on topics, but each small group present its point of view. And they are together. So and for us, it's less work to be done because we write a paper of like a longer abstract in some way. I think Laura can write something on heavy fermions. So try to put together a group of 5. You can ask a group of 5 or 4 to 4 by 4, so 16 pages or 20 pages. And you ask a group to write a topical review. And it will be very nice for the young people. I think young people they read less papers. So I think it will be very important for them to this kind of divulgation.
I started those topical reviews and reports on progress in physics a long time ago, and they were very successful. So I didn't know you were doing this, but I was editor-in-chief and editor of reports on progress in physics for a very long time. And we would run into people who would agree to write a review article, but it was too much work. Yeah. And then we started topical reviews. Yeah. But your idea is something I haven't heard of before, that I could be like an editor or write an introduction and get 3 or 4 people to write it. Yeah, that's a new idea. Okay. Okay.
And then the other can write 4 pages. And for example, for heavy fermions.
Do they have to be in different institutions?
It's not important. It's important is that the idea came from my passion for history of science. So Dirac had the one idea. Schrödinger has another idea. Pauli is writing another thing. Fermi is writing another thing. A Bohr said to them, write what you find and put together. At the end, you see that a different point of view converge.
That's neat.
You understand? Because if you write a review with 10 people, then you don't. There is something like homogeneous part. On the contrary, also differences between different groups is good in the same topic. It's been very successful in different, in complexity, journal complexity, they did another. So I've seen different plays, a little bit different from each one. But so the journal decided to accept this kind of new contribution. For this kind of conference on quantum material, I think it's a very good, for example, you can select what is Degiorgi, optical property that has been discussed. So, if we coordinate, it would be very nice results.
Well, So it's the end of our, like, one more working day. Thank you very much. And, okay.
It's been a long day.
It was a long day.